for solving limits of indeterminate forms. I'm your host, Dr. D. Okay, here we go. Now, back in chapter 2, we had this limit. The limit is x approaches to 0 of sine x over x. And there was a long involved proof there that said this thing is 1. Well, we have a much easier way of doing that today. We're going to be using this person's rule. Now, this person's name appears, if you're an English speaker, to be L. Hospital's rule. That is not the case at all. This guy is French, and his name is pronounced L'Hôpital. Here we have our L'Hôpital. Okay, so L'Hôpital's rule basically says that anytime you have a limit of an indeterminate form, then you can simply take the derivative of the top and the derivative of the bottom. Now that's not the quotient rule, that's just the derivative of the top and derivative of the bottom, then evaluate the limit. Now, an indeterminate form is 0 over 0. There's no way of knowing what 0 over 0 equals, a tiny number divided by a tiny number. Or infinity over infinity, or negative infinity over infinity, or infinity over negative infinity, or negative infinity over negative infinity. Anytime you have infinity over infinity, you may have 0, you may have an integer, you may have infinity. I mean, think about how many integers are there in, how many positive integers exist? Infinitely many. How many positive odd integers exist? Infinitely many also. But that's actually, if you go the total number of integers, or the total number of odd integers divided by the total number of integers, there are twice as many integers. So that number would be 1/2. Or total number of integers divided by total number of odd integers would be 2. Okay, infinity minus infinity. Well, if you just use that example I just gave, total number of integers minus odd integers would still be infinity. So, no way of knowing what infinity minus infinity is. It's an indeterminate form. Anything to the 0 equals 1, except 0 to the 0. That's indeterminate. Infinity to the 0. That's indeterminate also. Now, a large number to the 0 would be 1, but infinity to the 0, we don't know. Now, this last one is a really strange one. You think 1 to any power should be 1. Well, 1 to the infinity is indeterminate. Now, one warning. L'Hôpital's rule does not apply if you don't have an indeterminate form. If you have one of these red forms, then you can use L'Hôpital's rule. But if you have, let's say, infinity over 0, that seems like, well, you're dividing by 0, that's undefined. Well, yeah, dividing by 0 is undefined, but the limit as the denominator approaches 0 would be infinity. If you have an infinitesimally small denominator, you have infinity. That's not indeterminate, it's infinity. And 0 over infinity, that's not indeterminate either, that's 0. And infinity to the negative infinity, well, let's just check that out. Infinity to the negative infinity equals 1 over infinity to the infinity, which equals 1 over infinity. What's 1 over infinity? 0. Okay, so you need to make sure that you truly do have indeterminate forms before you're allowed to use L'Hopital. Now let's check what we have here. If I let sine x, if I let x approach 0, then sine 0 is 0, and I have 0 over 0. That is an indeterminate form. So I take L'Hopital's rule, and the symbol that says I'm doing L'Hopital's rule is to just put an H, a capital H, over the equal sign, and now I take the derivative of the top, and don't forget your limit statement, because we're not just evaluating the limit yet. So derivative of sine is cosine, and the derivative of x is 1. Now, I can evaluate this limit, because cosine of 0 is 1. So, I've just proven what we memorized from before, that the limit is x approaches 0 of sine x over x equals 1, by using L'Hopital's rule. Okay, let's try some more examples. How about the limit as x approaches 1 of natural log x over x minus 1? Well, if I just put 1 in for x, then I have natural log 1, which is 0, over 1 minus 1, which is 0. Once again, in indeterminate form. So, I take the derivative of the top and the bottom. Oh no, it's in red, how embarrassing. Okay, so, take the derivative of the top and the bottom, and the derivative of natural log x is 1 over x, and the derivative of x minus 1 is just going to be 1. So now I have the limit as x approaches 1 of 1 over x, which is clearly 1. Piece of cake. These problems are like tiny chocolate chip cookies. We need lots of them for a good snack.
That's the smartest thing I've ever heard anyone say about anything.
Yes, okay. So let's cruise on. Limit as x approaches infinity of e to the x over x squared. Now, e to the infinity would be infinity, and infinity squared is infinity. So, we have infinity over infinity, which is an indeterminate form. So we can take L'Hopital's rule. So we go, okay, L'Hopital's rule says, I take the derivative of the top, derivative of e to the x is e to the x, and derivative of the bottom is 2x. Now, notice, if I let x approach infinity, I still have infinity over infinity. Well, guess what? You're allowed to do L'Hopital's as many times as you want. It's L'Hopitalable. That's a word I just made up. Okay, so the limit as x approaches infinity of e to the x over derivative of 2x is 2. All right, now, when we let x approach infinity, we have e to the infinity, which is infinity. That's no longer indeterminate. It's infinity. Now, it's not a defined value, but we know for sure the limit as x approaches infinity of e to the x over x squared is infinity. Now, take a look at something here. If you look at the curve e to the x, it gets steep really fast. And the curve of x squared gets steep, but not nearly as fast. So basically, as we let x approach infinity, the top of this fraction is getting a lot greater, infinitely greater, than the bottom of the fraction. So that makes this whole thing infinity. Now, let's say, let's just do a different example here. What if we had x squared over e to the x? So let's just go x over e to the x. Save a step. X over e to the x. Now notice, as I let x approach infinity, I still have infinity over infinity. So I can do L'Hopital. So derivative of the top is 1, derivative of the bottom is still e to the x. Now, as I let x approach infinity, what do I get? 1 over infinity. Now, you don't say, oh, that's an indeterminate form. That's simply 1 over infinity equals 0. That's it, game over. Okay, now, the limit as x approaches infinity of natural log x over the cube root of x. So this is going to be infinity over infinity. And let's just rewrite this limit as x approaches infinity of natural log x over x to the 1/3. Okay, now when I can see it's infinity over infinity, so I'm going to do L'Hopital. And I end up with the derivative of natural log x is 1 over x, and the derivative of x to the 1/3 is 1/3 x to the negative 2/3. Okay, so let's evaluate this. The 1 over x really is x to the negative 1 over 1/3 x to the negative 2/3. All right, now, the 1/3 the 1/3 becomes a 3 on top. Now, remember how you deal with exponents. I subtract the exponents, but I want to go bigger minus smaller. So negative 2/3 is bigger than negative 1. So negative 2/3 minus a negative 1 is going to be 1/3. And that's a 1/3 on the bottom, because I started on the bottom. So notice then, I have 3 over x to the negative, or x to the 1/3. As I let x approach infinity, I'm going to end up with 3 over infinity, which equals 0. That's it, game over. Now, one thing, let me see how the book did that one. Yeah, okay. Basically, same thing. The just counting up your exponents, then you let x approach infinity. Okay, cruising onward. All right, the limit as x approaches 0 of tangent x minus x over x cubed. Well, let's plug in x equals 0. What's tangent of 0? I'll wait till you figure that out. Of course, tangent of 0 is 0. I would expect students who had a mediocre trig teacher to have a little trouble with that. But you, I happen to know, had an excellent trig teacher. Okay, so 0 minus 0 over 0 is 0 over 0, which is indeterminate. So, it's time for L'Hopital. So, oh no, it's in blue, how embarrassing. Okay, so we go limit as x approaches 0. Now, the derivative of tangent is secant squared. The derivative of x is 1, and the derivative of x cubed is 3x squared. Now, if I put a 0 in for secant, remember secant is 1 over cosine, and cosine of 0 is 1. So this becomes 1 minus 1 over 0, still indeterminate. So it's time for L'Hopital a second time. So the derivative of And let's see, I don't want to go derivative of secant squared. Secant squared minus 1 is tangent squared. Let's see. Secant squared minus tangent squared equals 1. So yeah, secant squared minus 1 equals tangent squared. So that means I've got tangent squared x over 3x squared, and I didn't actually use L'Hopital yet. Okay, now, we still have 0 over 0, so we do need L'Hopital. Okay, now the derivative of tangent squared, you've got to be careful with this now. So the derivative of tangent squared is really the derivative of tangent x quantity squared. So I do the chain rule, so I have 2 tangent x times the derivative of the inside, secant squared x. And let's change this to 2 times sine x over cosine x times 1 over cosine squared x. So we have 2 sine x over cosine cubed x. Now, this is getting ugly. Okay, so that was the derivative of the top. And the derivative of the bottom is 6x. Okay, now we still have 0 over 0 if we plug in our x equals 0. Was there an easier way of doing this? I don't think so. Let's just muscle through it. Okay, now, notice we still have 0 over 0 because sine of 0 is 0, cosine of 0 is 1, and 6 times 0 is 0. So we're going to do L'Hopital one more time. This seems to be a bit bigger chocolate chip cookie than we were expecting. Okay, now, we need the derivative of 2 sine x over cosine cubed x. So if f of x equals 2 sine x over cosine cubed x, then that means f prime of x equals low d high minus high d low. Oh man, the derivative of cosine cubed. All right, we got to do this. So cosine x cubed. We're going to take the derivative, and you end up with 3 cosine x to the second times the derivative of the inside, which is negative sine x. Okay, so low d high minus high d low. So this is going to be 3 cosine squared x times negative sine x, square the bottom, and away we go. All right. So now, that's the derivative of the top here. The derivative of the bottom is 6. Now let's clean this up a little. So we have cosine to the 2 cosine to the 4th minus, let's just do this. So it's 2 cosine to the 4th x minus, or that's actually going to be plus because negative times negative. So 2 times 3 is 6 sine squared x cosine squared x over cosine to the 6th x. And notice this whole thing is divided by the derivative of 6x, which is going to be 6. So I'm just going to go 1 over 6, or let's just put a 6 here. All right. And I hope we didn't make a mistake way back someplace and we're on a major wild goose chase. Okay, let's check this out now. As x approaches 0, cosine of 0 is 1. So this becomes 2 plus sine of 0 is 0 over 6 times 1. So this becomes 2 over 6, which equals 1/3. All right. Man, that was grisly. Let's look at example 4 in the book. What the heck did they do that made it so much easier than what I did? Yeah, that was definitely not an easy problem. They did it slightly differently without going to the sine and cosine. They kept it with secant and tangent. But it still came out majorly ugly. But we got the right answer, which is all that counts. Okay, so let's cruise onward. Okay, you could go back over the way I just did it, or you could look over example 4 in the book on page 310 and just see if you like the way they did it better. But, like I said, cruising onward. The limit as x approaches pi from the negative side of sine x over 1 minus cosine x. Now, let's look at the sine curve. Sine curve goes like this. So right at pi, right here, if I'm approaching pi from the left, then this is going to be approaching 0. The top approaches 0. Now if I look at the cosine curve, if I'm approaching pi from the left, the cosine curve is approaching -1. So basically this equals 0 over 1 minus -1. 0 over 1 minus -1 equals 2, and 0 over 2 equals 0. That's it. Now, let's say we blindly bumbled into L'Hopital. Let's say we didn't really check to see if it was in indeterminate form, and we did L'Hopital anyway. So what we're going to do is we're going to say, okay, take the derivative of the top and the derivative of the bottom. So derivative of sine is cosine. derivative of 1 is 0, derivative of cosine is negative sign, so we have a minus a negative sign, so we have a plus sign. And now when we plug in pi from the negative side, we have negative 1 over 0. Negative 1 over 0, that would be infinity. Or if I went, the limit as x approaches pi from the negative side of cotangent, that would be infinity. The answer is not infinity, it's 0. So, keep in mind, if you use L'Hopital's rule when you shouldn't, then you could be in a world of hurt. Don't let that happen to you. Okay, so notice, if it's not indeterminate, you cannot use L'Hopital's rule. If it is, you can, but in this case, it turned out not to be indeterminate. The answer is 0, not infinity. Okay. Now, the next problem we have is a 0 times a negative infinity. And that is an indeterminate form, but we need to turn it into a fraction in order to do this. So what we're going to do is we're going to make it the limit as x approaches 0 of natural log x over 1 over x. Notice all I did was turn this into a fraction. Now I have negative infinity over infinity, and I do have an indeterminate form, so I can use L'Hopital. But this first step was not using L'Hopital. It was just getting the expression into a fraction so I could use L'Hopital. So now when I apply L'Hopital's rule, derivative of natural log x is 1 over x, and the derivative of 1 over x is negative 1 over x squared. Let's just show that over here. Derivative of 1 over x equals the derivative of x to the negative 1, which equals negative 1x to the negative 2, which is negative 1 over x squared. All right, now this equals the limit as x approaches 0 of, flip the bottom and multiply, so we have 1 over x times a negative x squared over 1, and that's going to be negative x. Now, as x approaches 0, this whole thing approaches 0. That's it, game over. Okay, so cruising onward. Now we have the limit as x approaches pi over 2 from the left of secant x minus tangent x. Now, if we look at secant as 1 over cosine, then the limit, this is going to be infinity minus infinity. So that is an indeterminate form. Once again, we need to make a fraction out of it to use L'Hopital. So what I'm going to do is, hope I'm doing it the easy way and that we're not going to take forever here. Secant is 1 over cosine. And tangent is sine over cosine. So this whole thing is going to equal 1 minus sine over cosine. Now, as I let x approach pi over 2 from the left, I have 1 minus 1 over, oops, that's x. 1 minus 1 over 0. So 0 over 0. So I can now use L'Hopital. So L'Hopital in it, remember, always keep the limit statement in every step until you evaluate the limit. Now, the derivative of 1 is 0, derivative of sine is cosine, so we have a negative cosine x on top, and the derivative of cosine is negative sine x. And so this becomes the limit as x approaches pi over 2. Well, let's see, if I just negative over negative is positive and just evaluate the cosine at pi over 2 is 0, sine at pi over 2 is 1, 0 over 1 is 0. Or the other way I could do it is say the limit is x approaches pi over 2 from the left of cotangent x, which we know equals 0. So that's it, piece of cake. Okay. Just checking if I did the way they did it in the book. The heck? Where did they do that? Oh, here we are. Yeah, okay. So I did the way they did it. All right, now, last two. Here we have a different type of indeterminate form. Remember in the beginning of the lesson, I showed you the indeterminate forms that are fractions. Here we have infinity minus infinity, we turned it into a fraction. But now, when we have exponents, it's a different deal. Now, we know from dealing with logarithms that that's the way to get a variable down from an exponent. No difference here.